Welcome everybody back to section 3-8 and moving on and wrapping up the chapter. We're going to talk about perpendicular lines right on the heels of talking about parallel lines. That would sort of make sense. So at the top of your paper there for number 1 you have a definition of perpendicular, which as you see by the smiley face needs to go on your justification sheet. And we're used to this one again from algebra, just like we are with parallel lines, but here we want to pay special attention to what do we really mean by the definition. So the first thing is that this definition is about lines or segments or rays and how they meet up. Okay, so even though we may think of perpendicular lines in terms of being 90-degree angles, that is true, but it's not really about the angle so much. It's a statement about what is perpendicular. And the lines are perpendicular, or we would say the rays are perpendicular, or the two segments are perpendicular. So we talk about a polygon, and it has these sides that are segments. We would say the angle is 90 degrees, but we would say side A and side B, okay, are perpendicular to each other. So that's how those two go together, the angle and the sides or the segments there. And then for number 2, two different ways, and I drew some arrows on your paper there, but so maybe off to the side of your paper, okay. The drawing part of it would be, if you have two rays like that, you could say they are perpendicular by putting the little symbol for 90-degree angles in there. You could do the same thing with lines or segments like I did up there with the polygon, or two lines that intersect could also be signified as being perpendicular. So we would say line M is perpendicular to line L, and so that's the drawing part of it. In a sentence is kind of what I just wrote right there, and we read it like a sentence. Line M is perpendicular to line L, okay, and so that's why I called that one how we would use that in a sentence. But that little notation right there really is a whole sentence, okay. So two different notations, you can kind of fit that on your paper wherever it makes sense to you, okay. But all of that kind of coming from the definition, or what we use as far as notation goes for perpendicular. All right, and then two more things that need to go on your cheat sheet, and I think there's only one drawing on your paper, so you might want to add another drawing for each of these if you have some room. But if you don't, I would encourage you just to write down this kind of simplified version of each of these. Okay, I put it in words because the book has it in words as well, but it really, once you understand the notation, I think the words will come pretty easily. So if two lines are perpendicular to the same line, then the lines are parallel. So there's a lot of lines going on in there. So if you take the given, and so if we go back to thinking about antecedent and consequent, and right, and this is where really knowing what we mean by that, the if part and the then part, here's the antecedent, and the consequent there is what we're going to end up with. So if we mark the given on our picture, then it would look the way I have it marked here, that line R is perpendicular to line S, okay, and then line T is also perpendicular. And so when we look at the graph of what we have right now, or we look at the figure, the two symbols that are on the picture right now are two perpendiculars. And so that's kind of where the name comes from. The name for these two theorems, the name comes from the given, comes from the antecedent. So if we stop, and I would probably encourage you just to go ahead and memorize these two. I don't usually say that for all of them, but these two, they're so close and they're so easy to mix up. It's probably best if you can just memorize it and kind of jot it down, even in notation like this. So R is perpendicular to S, T is perpendicular to F and S, and so what we're given are these two perpendiculars. Well, from that, then, we're able to conclude that these two lines must be parallel. And so our conclusion, okay, is these little parallel symbols, and I kind of briefly talked about that, but in the book talked about it, so you'll probably run across that. So just make sure you don't think that those are just misplaced arrows. Those are actually telling you something. Those two little extra arrows on the lines are telling you that they're parallel. Okay, so there's a notation for that as well. All right, so that's one version, the two perpendiculars theorem. The perpendicular to parallels theorem follows that same general pattern, is that we want to focus on the antecedent. And so the name, once again, comes from the antecedent. We're given a perpendicular, so the way I have it marked here, again, that line R is perpendicular to line T. And the second part of the given is that R and S are parallel. And so if that's what we're given, then what are we left to be able to conclude? And in this case, we have this rule that we just learned about corresponding angles, that this northwest, for those of you who like directions again, corner would have to correspond to this northwest corner, and so those have to both be perpendicular. They have to be equal by the parallel lines corresponding angles postulate, and so therefore it's got to be perpendicular. So if both of those angles are 90 degrees, then those two lines, T and S, have to be perpendicular. So those can be confusing, and like I said, this might be actually a good case where you just go ahead and memorize those two. But if I could give you a hint about memorizing them, it's that they're named for the antecedent. The given information is how you're going to remember, how you're going to associate that name and tie that together. We're going to spend some time on Monday reviewing, so we'll kind of hopefully get to practice how to use all these different things. All right, the questions that are on your paper here are actually about solving things, so some more algebra problems. And so in number 3, if we know that we've got this perpendicular sign, so GF and EF are perpendicular, then we know that angle has to be 90 degrees. So we can take 4x plus 2 and just set it equal to 90, and then go ahead and solve. And so remember, I'm going to go a little bit quickly so the videos don't go so long. So if you need to backtrack at any point, you can pause, or you can pause it and go ahead and work through it yourself, and then come back and see how the answer is. So, and then divide by 4. And that's where we're supposed to end for that one, solve for x, and so I'll have to even go back and plug in that case. All right, take a look at number 4, and we'll just take your numbers there and write that on the picture. And then also take note that you have a 90-degree angle in there, so this guy is 90 and UVR is 54. And those 3 angles together have to then add up to 180. So you could just take 90 from 180 and then 54 from 180, and you know that x will have to be 36 degrees then. 180 minus 90 minus 54. All right, and number 5, there seem like there could be a lot of ways to go about this, but if we're not careful, we'll set up an equation that won't really lead us where we want. So what we want to think about here is that if these two things are perpendicular, then angle 1 has to equal 90 degrees, and angle 2 has to equal 90 degrees. If it would seem logical to say angle 1 plus angle 2 has to add up to 180, or to set them equal to each other. But then what ends up happening is your algebra actually kind of tricks you, and you solve for an A. You solve for a value of A that actually makes it true, and that's not actually what we're after. We're trying to see if these two expressions will give us the same result of 90. And so what we want to do is set them each equal to 90, the two separate expressions. And so variable 1, this, and then variable 2, we have that. And then you can pause again if you want, go ahead and solve, and then come back to see if you got the same result. Distribute. Subtract 42 from 90, and divide by 2. And so over here we get that A would be 24. Over here, we get that A. So A equals 12 and A equals 24 are not the same, and so our A's here do not turn out to be the same. So no, even though they look like they're drawn to be perpendicular, they actually are not. Number 6, these kind of carry over one after the other, and now we're looking to kind of justify or use the theorems and definitions that we just came up with. So A is perpendicular to C. Yours is a little more tilted than mine is. A and B are the ones that are parallel, or the ones we're going to try to test to see if they are parallel. And we're given that A and C are perpendicular, and that angle 3 is equal to angle 4. And since they're a linear pair, that means that they both have to be 90 degrees as well. And so once again, we have the corresponding angles. So if those are both 90 degrees, then these guys are indeed perpendicular. Okay, so are indeed parallel. So for part A, you could say y is B perpendicular to C because of the definition of perpendicular. Okay. That if 3 and 4 have to be equal, then they have to each be 90 degrees. And then the second one, once we know that we have two perpendiculars, so let me erase and go back here because we really end up with is that A is perpendicular to C, and B is also perpendicular to C. And so now what's marked on our picture is two perpendicular symbols. And so by the two perpendiculars theorem, yes, we are able to say that A and B are parallel. That A and B are parallel. All right, on the back, I want you to take a minute and see if you can't make some sense out of that. And at the very least, you should always go through the given and mark that on the figure. So take a second and do that. Okay, so that's what you have, and I kind of switched colors there to show that there are really three separate things going on here, and now we're going to start drawing some conclusions. And so we've got a little set of matching or multiple choice you can go through. So why can we say, from this given information, why can we say that MN is parallel to ZY? Well, we got a middleman up here. Okay, so since each of these, N is parallel to WX and ZY is parallel to WX as well, then these guys have to be parallel to each other by transitivity of parallelism, so that's D. Number 8, why would we be able to say that zy is perpendicular to xy? And so in this case, we have a parallel set and a perpendicular set. And sometimes it helps to just extend them past a little bit. Maybe helps you think of them more like lines. So here's the two parallel lines, and then there's our one perpendicular. And so if we have a parallel and a perpendicular given, and we want to conclude that this guy, therefore, has to be perpendicular. That's the perpendicular to parallels theorem, so that's E. Angle WXY is a right angle WXY. And it might be easy to jump to the conclusion that that's the definition of right angle because we think of that as the right angle symbol, but in this case it's not one of your options. So the other time that we use that right angle symbol is when we're talking about lines that are perpendicular. And so even though here we're talking about this angle is a right angle, the lines or the sides or segments that form it are perpendicular. So we're going to use the definition of perpendicular. So based on what we were given, that WX is perpendicular to XY. So what was given? You always got to go back to what's given. What we're given was this statement about the lines being perpendicular. The symbol we used doubles as a right angle symbol, but in this case, because of how it was given to you, it's considered perpendicular. And then the last one, W, graph's getting a little messy here, W, M, N, and M, Z, Y. Why are those two guys equal? And so always kind of ask yourself, how are they related? This is the one we just learned in section 6. These are corresponding angles because these two lines are parallel. And so once again, I think it helps if you extend them out past and then you focus on this guy right here, and that's the transversal. So to use some of our words from section 6 that we have to start getting familiar with, okay, kind of focus on the green there. And so we have two lines being intersected by one other line, and those are corresponding angles. So given that the lines are parallel, we conclude that the angles are equal. And so B and G, both of which are the same theorem, but you have to pay attention to the order. So we want to start with the lines being parallel, and our conclusion is that the angles are equal. So we want to pick that one in the right order. Okay, that's more of what we're going to work on Monday. So I know that's all very new. I know it's maybe troubling, okay, but do your best to kind of just trust that we're going to keep working through it, and we'll do some reviewing on Monday. That should help get us a little more practice at it. Okay, with practice we can figure it out. The last two you can put in the space down here at the bottom of the page. These also need to go on your cheat sheet. Very similar statements to what you learned in algebra, but relating slope to being parallel and to being perpendicular. And this little statement about lines being perpendicular, okay, the product of their slopes is equal to -1. You'll also see it written M1. Remember, M is slope. M1 times M2. M1 times M2 equal -1. And you probably learned the phrase opposite reciprocals. And that's really what ends up happening if we take, say, a slope of 3/4 and we multiply by the opposite reciprocal. So opposite meaning opposite sign. Reciprocal means we flip that over. Then we'll get a product of -1. And so when you're asked to verify, or you're asked to actually show that these lines are perpendicular, this is what you want to write. You want to actually use the slopes and show that their product turns out to be -1. In our minds, I know we've learned it as kind of this little saying, opposite reciprocals, but we can also use it now in this theorem to actually come up with an equation or a justification for that. Okay, so make sure those two also get added to your cheat sheet. And thank goodness we were done with that chapter. There were so many things to add to our cheat sheet. So we'll keep working on it. Again, I'd encourage you to spend a little time with it every couple of days so it's all fresh in your mind. You do not need to do this homework. We're going to be working on it in class, so it's not really homework. It's going to be in-class work. Okay. All you needed to do is finish taking notes, but you do need to pay attention. You should have a protractor already, and you do need a compass by next week. And you'll be very, very lost if you don't have one to use and work through the examples that we're going to do together in class. We'll spend some time reviewing on Monday, and then quiz on Tuesday. All right. See you soon.